All right. Let me check my mic, make sure it's good. Test. Yep, it's working. Test. Yep, working here. Well, it is noon, and I am going to get started. All right. So I did send a link to Chris, and he has to read the message from Canvas. He got it? Okay. But I don't see him here. Oh, he is not joined. Okay. This is the problem that I have, in the previous class is I don't know how to. Oh, okay. I just got the prompt here, but I don't see where the prompt is, to add people to. Oh, admit. There we go. All right. Okay. So Chris is in. Okay. All right. So we are going to continue with the set notations today. And then today we are expanding on things that we have already talked about. The one last thing that I need to do is to talk about a set containing another set. So that's going to be the focus at least at the beginning of the class, and then we'll see where we can go after that. So we are still using the same module, but I've been expanding the module itself. So even though it is still the same module, it does have new information. And this is the latest part that is a new, the latest addition. So given that we have two sets, X and Y are both sets, then X and Y are considered the same or equivalent to each other if and only if X is a subset of Y and Y is a subset of X. Okay, which is also saying X is considered equivalent to Y if and only if for everything in the entire universe. Okay, X in X, E in X, sorry, E in X if and only if E is also in Y. So anything that is in X has to be found in Y. Everything that is in Y must also be found in X. That's kind of the general idea of how we can compare two sets. And once we have that definition, which can be recursive, okay, because an element of a set can also be a set, okay, then we can talk about, how we can have a set as an element inside another set. Are we good so far? Okay, all right. So now we move on to the examples, and I'm going to use Joplin again, to kind of look at the examples. So give me a second here to start up Joplin. If it's not already up, it is already up. Okay. I'm not surprised because I don't usually close things unless I have to. There we go. All right, so we are just continuing with the examples that we have already talked about, in the previous classes. So I'm gonna, talk about this. Okay, so we'll start with something that is, I would say, kind of somewhat in the boundary case. So we are looking at this. Okay, give me a second, and I'll try to address the question. Uh-huh. Nope, nope. An element of is different from subset of. So we'll take a look at a few examples. Huh? Mm, hmm. Well, when we get to that point, we'll address it. Okay. So right now we're just going to look at the cardinality of a set where the empty set is an element of that set. Okay. So now the question is, what is the cardinality in this case? In other words, how many things are in the set? There's one thing, exactly, because that one thing is the empty set. So the empty set itself is an element of the set that we are dealing with here. Okay, very good. And next question. Okay, the next question is this. Okay, I have to use that. Okay, Okay. So what is the answer to that of what is the value of this expression? It is true. Very good. Okay. So it is true. And let's modify this a little bit and ask that question again. But this time it is, oops, YYP. There we go. What about this? There we go. This is false. The empty set is not an element of an empty set because nothing can be in an empty set, including the empty set itself. Does that make sense? Okay. So now we are we ready to move on to some examples that are more confusing? Okay. I like the confusing examples because if you're confused, that means there are certain concepts you have to kind of really differentiate from each other. And if you're not confused, that means you probably understand the fundamentals of these ideas. Okay, so let's go ahead and start with this one. So we'll have, I'm going to name two sets here. Okay, so we have set X being, just with an element of A, and then we have set Y here, which is a set that has A in it, but also a set that has A in it. Okay, so I'm going to pause right now and see if there are any questions about how X and Y are defined. How many elements are in Y? Two elements, that is correct. Okay, very good. So with this, now I can make some subpoints and then I will ask some questions here. So I can now ask, is X an element of Y? This is true. Okay, very good. And I'll ask another question, which is X a subset of Y? It is also true. Very good. Okay. So is that always the case? If a set is a subset of something else, it is always an element of that something else? The answer is no. Is it always true that if a set is an element of another set, it is automatic that the first set is also a subset of the second one? The answer is also no. Okay, so I just crafted an example to make it as confusing as possible, given everything that we have talked about. Yes. Okay, so okay, so I think the core of your question is this. Okay, so what Ilya was talking about, I think, okay, correct me if I'm wrong, is whether A is the same as the set that has A in it. Okay. And what do you think is the answer to this one? I'll put parentheses around the whole thing. So what is this? It is false. Okay. A value does not equal to a set containing that value. Yes. So if we are asking whether something is in another set, we are asking whether that whole thing is found as one element of the set that we are concerned about. Okay. In what case? Yes. So in this case, it is also a proper subset. So that means we can also say that X is a proper subset of Y is true because, oh, wait, hold on a second here. In order for X to be a proper subset of Y, there has to be at least one thing in Y that is not found in X. Can someone tell me what that is? Hmm? Would it be A or would it be the set of A in it? It will be just A. That is correct. Okay. So A as an element is in Y, but it is not, it is all, wait. Okay. It is the set that has A in it in this case. In other words, okay, to make this clear, okay, to make this extra clear, let's look at this. Okay, so we'll look at Y minus X, okay, because this will make it very clear. Okay, what is that? Not A, the set with A in it. There you go. All right, so I think these examples help to illustrate what do we do when a set contains elements that are also sets. Are there any questions? Yes, that is correct. Okay, so let me put it into your actual examples. Okay, so we'll distill everything just to down to what you're asking. Okay, so that means the cardinality of and I'll make this as simple as possible. So, okay, so you're basically asking what is the answer to that question? What is the cardinality of a set where it contains an element that is a set with three elements in that one? The correct answer is one. Okay. Yes. Okay. So think of this as a folder structure. Okay. So you have folder one. Okay. And I'm going to use, uh, okay. I'm trying to think of the best way to illustrate this. So I will use my file manager. Okay. So file manager. Okay. We'll take a look at this one. Okay. Make the whole thing fit. There we go. And I'll create a folder just for this illustration. So file, create folder. We'll call this set one. Okay, so set one is a set. Okay, so in here, I create another folder because every folder is a set. Okay, so I create another folder here. I'll call this set two. Inside set two, I create three actual files. So I will say create document, empty file, call this element one. Oh, okay, I cannot spell, but that's kind of besides the point. Okay, element two, and then we have finally element three. Okay, there we go. Okay, so now from the perspective of set two, obviously it has three items in it. We good? But when we look at the perspective of set one, how many things are in set one? There's only one thing. Now, that thing by itself is a folder and it has some items, but those items inside the subfolder does not count as things inside set one itself. So is that concept okay? All right. And but in set one, I can also create additional individual files. It's not a problem. Yep. Hmm? How do we express this using the cardinality formula? Mm, so okay, I just think of a few different ways. I'm trying to think of a few ways to kind of describe it. Um, the cardinality is a single level counting. So we are not recursively counting what is inside the nested structures. So is that sufficient as an explanation? In other words, in this case, we are only looking at one level down from the actual set that we are taking the cardinality of. So the set that we are taking the cardinality of only has one element, which turns out to be a set itself, which is the inner brace. And the inner braces, the pair of inner braces is enclosing A, B, and C, but those are at a sub level. We are not concerned at the top level. Yep. I would not use children nor subset to describe it. So A, B, and C are elements of a set, and that set turns out to be an element of another set. A set is a folder. So A, B, and C in this case are files. They're not folders. If they were folders, then they can still contain additional items, and we don't really care because at this point, I'm just asking what is the cardinality of the set that contains an element that is a set, and that's all I need to know. It only has one element. Okay, so let's push that. Okay, so because I like the boundary condition kind of thinking. So if I were to look at this, okay, this is the set, okay, math BBZ. Okay, all right, so let's take a look at this. Okay, first of all, what does this represent? If you are frowning a little bit and thinking, I'm not sure, or thinking that tech, you never taught us that, you might need to review the material a little bit more often. Okay, so what is that? Go ahead. The set of all integers. Okay, so Z is the set of all integers. So the cardinality of a set that contains the set of all cardinalities is 1 because Z is considered as one gigantic, infinitely large container. But nonetheless, it is a container that is inside the outermost set. Is that okay? So that's you're pushing the boundary condition a little bit more to outward. And this is actually not much different from this one over here, all the way to the top. What is the cardinality of a set that contains the empty set as the only element? Well, that's all I need to hear. As the only element, I don't even care what it is. The set only has one thing. The cardinality is just one. Yes, go ahead. The set, correct. Yes, that is correct. All right. So can you guys think of more examples that you want me to evaluate? You can always give me some expression to evaluate. Yep, go ahead. Okay, X is the set, a set that has AB. Okay, and then Y is, do you want to write it on the whiteboard so I can transcribe it into into Joplin? Okay. Otherwise, I can give it a shot. Okay. So X is a set that has AB in it. And what is Y again? Like that. Okay. So I just want you to double check before I say something about this. Sorry. X is not in Y. Okay. All right. So we take X out of Y. Okay. Fine. You mean like that? Okay. And what are the sub questions about this? Okay. So the question is X. Okay. So the question is what operator are we using in or are we using subset of? Is an element. Okay. So that's the question. All right. What do you think? This is true. It is true. The set that has AB in it is indeed an element of Y. I would not make that, comparison because those things are a little bit different. So the set notation is really just containers, right? So X is a container that contains two things. One thing is called A, one thing is called B. Y is also a container that contains another container that contains A and B in it. So the equivalency is X as a container that contains A and B can be seen as an element of Y, which is a container that contains exactly that second container. As I said, I would not use the concept of an array, versus a vector versus a matrix to describe this. Yeah, because there are very tricky situations where I do not want to kind of get into, and the best analogy is really a file versus a folder. Yep. All right. So are we okay with these concepts? Okay, cool. And if there are any questions, if anyone is feeling uncomfortable with these things, you should come to my office hour. Okay, because I can further explain these concepts, or I can give people some ideas of how to approach things that are abstract like this. Yes, go ahead. The reason why I said it is kind of like the number of items in an array is because what do you do with a set that has an infinite number of items? Like the cardinality of R, which is the set of all real numbers, versus the set of all integers. So how do you compare those? Well, the thing is, you don't compare infinity with infinity because infinity is not a number. You cannot compare. And that's why cardinality is kind of like the number of items, but not exactly that. So when your set has a fixed number of items in it, then yes, the cardinality is exactly the same as the number of items in the set. But if you have a set that has an infinite number of items, then you cannot look at it that way. Because then you cannot compare the cardinality of integers versus the cardinality of natural numbers. Okay, so we'll deal with that comparison after we talk about functions because we need concept of a function in order to talk about that. Okay. Any other questions? Yep. You mean here? No, it would not be equal to one. So you're talking about removing the braces? Okay. So we are fast forwarding a little bit here, but I will kind of talk about this so that this way, for those of you who actually try to relate concepts as much as possible, then later on when we do get to that point, you go like, oh, okay, so that's what we were talking about. So if you are just looking at the cardinality of the set of all integers, okay, it doesn't really have a particular number, but it is called aleph no, aleph 0. That's the representation. So you go like, well, does that mean aleph no is infinity? Nope, that is not the case either. It is just a symbol. All it is this is by definition. Aleph null is the cardinality of the set of integers, or you can look at it as the cardinality of the set of natural numbers. Okay, so when we get to that module later on, I would say in about 2 weeks or so, then we'll talk about, what that actually means. Okay, yep, yes. So I think the real number is aleph 1, so aleph 0, aleph 1, and so on. So there are different levels of infinity, basically, so to speak. Yep. Yes, it is. Technically, it is called countably infinite. Okay. And the key is countable, as opposed to the set of real numbers is infinite, but it's also uncountable. Yep. Well, we will get to that concept later on. Okay. I cannot talk about it until I have talked about functions. So very good. You can write it down, kind of as a note and go like, okay, this is a question, okay, because it's a good question to ask. We just don't have the right tool to explain it right now. Okay, very good. Any other questions? I like all of these questions. The process of asking questions is important when you are trying to learn something. Okay, you're basically asking what if, what if, what if, based on what I have observed here. These are all kind of boring, simple examples. But what if this? Okay, what if this? What if we're dealing with this complex, thing? So those are all very good exercises to do as you're learning your new concepts. All right. Any other questions? No other questions? So I know it may not be as appropriate to bring up this topic in CISP 440, but since I have it already done, I might as well reuse it. So let me go back to the browser and go to ChatGPT because I was teaching CISP 300 earlier today. And unlike when you took CISP 300, I am already talking about BNF, which is Becker's NOR form, which is a meta syntax to describe syntax. And I'm also trying to make a correspondence between the syntactic um, representation of a conditional statement versus a flowchart. Okay, so you would say, okay, that's brutal, for CISP 300. Well, to me, it is not brutal. The way I would describe it is front loading. Okay, look at that word if you're not understanding that word. Front loading means putting the more fundamental, difficult stuff up early. And I think that's probably a better way to do things so that we don't necessarily convince people that they can do something when they may not be able to do it or they don't yet have all the skill sets to deal with it. All right, so this is the one thing that I asked ChatGPT this morning. What are some of the difficulties of learning abstract concepts such as the syntactic rules of a programming language? But the whole point is computer science is going to be a little bit on the abstract side because it really is applied math. Okay. In other words, people who do not like math, will have to overcome that difficulty, okay, to make themselves more comfortable with mathematics. So this is kind of interesting. It talks about, high cognitive load, remembering syntax, semantics, and structure simultaneously require managing multiple layers of information at once. So it is true, okay? When you learn a new programming language, especially a programming language that has different constructs or different concepts compared to the ones that you already know, okay? It is difficult because you have to deal with the syntax side and also the semantic side at the same time. So what do you do? What what is the shortcut to learn something that is abstract? Okay, I was about to say the empty set. There's no such thing as a shortcut. The set of shortcuts to learn something abstract is an empty set. There is no shortcut. There's no shortcut that you don't have to pay a lot more later with interest. Yes. Yes, but you need to know the fundamentals first. So I think that really is the answer, is you have to understand the fundamentals. Okay, how many people in this class? Okay, go ahead. So there are always the three questions, the what, the why, and the how. They're all important. When you're learning something, they're all important because the what gives you the ability to describe it to somebody else. Okay, you can name that thing. The why connects the concept to something else that you have learned already, and it specifies how this thing relates to everything else. And the how is the mechanism. It is the kind of down to earth actual mechanism of the thing. It's the mechanics of what you're learning. So all three questions are actually important when you're learning something new. And sometimes, when we teach math, we teach something that's kind of like an island. It doesn't seem to relate to anything else, and that makes it difficult to learn because we don't know why we're learning it. All right. So, anyway, the reason why I'm bringing this particular conversation up is, just to re-emphasize that this class is abstract. Computer science is abstract. There are a lot of things that are not very grounded, and you need to have the ability to understand abstract concepts in order to proceed. Okay. All right. Any other examples you want me to look at, based on what is already here? Okay. If there are no additional questions, yes, go ahead. Hmm. How do you specify recursiveness? When it comes to processing everything, kind of, you're doing basically a depth first search. Well, we first need a predicate to know whether something is a set or not. Okay, so let's go ahead and talk about that. So let me kind of rephrase the question so that we know what Elia is talking about. Ilya. Um, okay, so we want to process everything that is um, inside a set, and we want to do it recursively. Okay, that's kind of the premise. And the way to do that, let me see what is the best way to do it. Okay, we can do it over. Hmm. Okay, we'll do it over here. Okay, so we are going to say um, assume. Okay, I'm inventing a predicate here. So I'm going to say assume um, math RM is a set of X is a predicate that returns true if and only if X is a set. Okay. So in other words, it's a type checking kind of mechanism. It returns true if and only if X as a parameter is a set. For everything else, it returns a zero. Yes. Wait. I'm not done yet. Okay. So the algorithm to do the recursive thing is to do something like this. So if I were to code it in pseudocode, okay, so I'm going to use pseudocode here and I'm going to borrow syntax from C. So the way you do this is you say for each element E in whatever set X to begin with, because you have to be given a set to begin with. So you do this. And then inside the loop, okay, I know you guys probably want to do it like this. And because it knows C syntax, it just wants to format it in a certain way. So now we call this function um, process, okay? And X is one of the parameters, and then we have a callback, which is the callback function that specifies what you want to do for every non-set element recursively within the entire thing. Okay, so now we say if is a set E, then we just recursively do the whole thing. Process E callback, else we just use the callback on whatever E is. So we just say callback E, and that's it. I think I'm probably missing one more level of parentheses or braces. That's it. Does that make sense? Well, math notations that we have talked about up to this point is not procedural. They do not describe how to do something. They describe whether something is true or not and return the value. So there's no math notation that can really represent this. So math notations are all about you give me an expression and the expression gives you back a return value. So it does not have the mechanism to say, okay, let's do this abstract operation or callback function, however you want to call that, to a particular thing. So the math notation that we know of has no such thing to describe this. Okay, so I think that answers the question. Okay, all right. So what are we going to do next? We are moving on. Okay, all right. So what about those people who think, well, tech, that's not a whole lot of examples. I don't feel this is giving me enough chances to practice, what I think I have learned. So what are we going to do about this? Yes, exactly. You ask ChatGPT, and I made it easier. I'm not sure whether I shared this with this class or not. Do you guys remember that I talked about this button? Yep, there you go. So use that button, copy the entire content in Markdown, and use the phrase or the prompt that I have already suggested, and kind of do it that way. Okay. All right. So now we are moving on to the next module, and I hope some of you have a chance to kind of read a little bit ahead. And by the way, all of these ones here, they all have little exercises at the back. Okay, at the bottom, and these are deprecated, but it doesn't mean that they are wrong. Okay, so if I were you, I would still read at least some of these and at least scroll all the way to the bottom and do the exercises that is already there. So let me show you one of these, okay, and show you what I mean by that. So this is old notations, I mean old explanation, but it still has questions. Okay. So now we can look at each one of these and go like, okay, so under empty set, okay, what is the question? What is the symbol for an empty set? What is the significance in empty set theory? And then the answer is blah, 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 blah. Okay. So I would still kind of pay some attention to these modules, even though they are deprecated, they still contain valuable, questions and answers to the questions so that you can practice. Are we okay with that? Okay. All right. So now we are moving on to the next big module. Big operators, we will skip it for the time being, okay? And then, so the next one up is functions. So function as set. So we'll take a look at this one. All right. So the first thing it mentions is the concept of a tuple, which we have already mentioned, okay? So a tuple is also a container, but in this kind of container, ordering is important, and you can also have multiple elements in the container of exactly the same value. So that means the three tuple of 1, 1, 2 is perfectly okay. It is a tuple that has three items. The first item is a 1, the second item is a 1, the third item is a 2. Yes. Nope. There's no type constraints in mathematics. Yep. So they can be anything, including another tuple or another set. Okay. So anything can be a member of a tuple. And a tuple can also be a member of a set or a member of another tuple. So everything can nest. There's no restriction of what can nest within what else. All right. And in this notation, I usually use T bracket I to indicate that we want to get to item I of the tuple, but I is going to be zero oriented. So that means the last item is the number of items minus one. Okay, but you know that already because it's the same convention as in C and C++ arrays. So now we get to the concept of a function. Yep. C++ is zero oriented when it comes to indexes. So the index of the last item in an array is the number of items in the array minus one. Hmm. Okay, if your array has 5 items, the first item has index of 0. the last item has an index of 5 minus 1, which is 4. That's what I'm trying to explain. I don't understand why you say that it does not work. Okay, you have 5 items in an array. The first item is index 0, the second item is index 1, then you have index 2, index 3, and the last item has index 4. 4 is inside the square bracket if you want to specify the fourth element of the array. I mean the fifth element in the array. Okay, I think we may not be talking about the same thing. You may be talking about the number of bytes needed or something like that. Nope, not in C++. But this class is in the context of C++. So don't bring up your Python examples. Okay, ignore everything that has to do with Python. How about that? We just filter all that out. Not in C++. We only know C++ here in this class. Hmm? Exactly. What is Python? I think it's a kind of snake. There's another programming language called Cobra. All right. So let's talk about functions. Okay. So we learn functions in other math contexts in a certain way, but in this class, the way we talk about functions is like this. So this is a notation. I'm skipping a little bit ahead, because the rest is really just kind of verbal explanation of the same thing. So if I use this notation, it is kind of a question. It is asking, is f a function where x is the domain and y is the codomain? Okay, so let me explain each one again. This notation is kind of a question. It asks whether f is a function where x is the domain of f and y is the codomain of f. So those are the terms, okay? And now obviously you guys will go like, what does it mean? Okay. Well, what it means loosely, okay, if I were to use just English words to describe it, it means f is a function that maps elements of x to elements of y. Okay. So, okay. So that means you can make an arbitrary function and you can kind of select your own domain and you can then select your own codomain and then you can select also how things are mapped between the domain and the codomain. Um, all right, so we look at a regular function like this, okay? F of x equals to 2x. Does everybody understand the definition of this particular f function here? Because that's a very conventional way to define a function. So what if I were to tell you that x has to be an integer, okay? In other words, this function, even though it can work in real numbers too, but I want to restrict this function to only work with integers. You go like, okay, fine, because for every integer x, I can find twice of that integer, not a problem, okay? So that means in this context, I can also use this notation here to say that this function, f, is a function that maps from the set of all integers to the set of all integers. For every integer, I can find twice the value of that integer. And that's the job of this function. Are we good so far? Okay, so that's just notation. But one thing that is starting to become different from this class, with this class compared to your other classes, is the function f here is now seen as a set. It is a set of two tuples. In other words, every element of a function as a set is a two-tuple. When you have a two-tuple, you have two things. The first thing is always something that comes from the domain. The second thing is always something that comes from the codomain. In other words, every tuple is telling you exactly how to map one specific value from the domain to a value in the codomain. Is that okay? Yes. Codomain. Yes. Mm-hmm. So now we look at this thing here, okay? So what that means is I'm defining a set. In this case, F is a set. And this is one way to look at the set F here. This is one way, this is the other way, they're equivalent. So I would look at the second one, this one here. For every x as an integer and for every y as an integer, y equals to 2x if and only if xy is in the set F. So a function is both quote unquote a function, but it is also a set at the same time. Yes, yes. That is how we are going to look at the concept of a function in this class. A function is a set where each element is a two-tuple. The first item of the two-tuple comes from the domain. The second item of the two-tuple comes from the codomain. Now, those are kind of loose ways to describe it, okay? So I'll describe it in much better ways in a much more concise way later. Go ahead. So when you use the word range, it means the same thing as a codomain. Mhm. Well, in this class, we don't care about linearity. So that means, what you choose to be in the domain or what you choose to be in the codomain can be totally random stuff. They may not even be integers. They may not even be items that can be sorted, that are ordered. So it's a very loose way of defining a function in this class. I'll show you guys some examples. Yes, go ahead. Mm, no, I would not see it that way. It's a two-tuple where the first item comes from the domain and the second item comes from the codomain. No, the first item comes from the domain and the second item comes from the codomain. We boil everything down to the set notations, things that we have already seen in this class. Now, in your own mind, if you want to use different analogies, that's okay, okay? But that is not how I would explain the concepts. Yep, go ahead. For every x in as an integer in the set of integers, for every y there's an element in the set of all integers, y equals to 2x if and only if xy as a two-tuple is an element of f. This is how we describe the function that we describe in some other way up there. So you can see that I am reusing the notations that we have already introduced, and I hope it is consistent. Okay, which also means getting familiarized with the notation is really important. All right. Okay. Are we ready to move on to the next section, which starts with a question of that is kind of confusing because it looks like a loop. What makes a function a function? Are we ready? All right, let's go. Okay. So if we know, okay, that f is a function that where x is a domain and y is a codomain, that means f has to be a subset of the Cartesian product of x and y. Okay, let's digest that a little bit. Okay, if we know that f is a function where X is the domain and Y is the codomain, then we automatically know that F has to be a subset of the Cartesian product between the domain X and the codomain Y. Okay, so are you guys making that connection? Yes, yes. So this part here means, if you already know that F is a function, and you know X is the domain of the function and Y is the codomain of the function, given that those are the given conditions. Don't ask me why I know that, but given those are the conditions that you already know that you're given with, then we automatically can conclude that F as a set is a subset of the Cartesian product between the domain and the codomain. Mhm. But is that clear? Does everybody make the connection between what we have described a little bit earlier and the conclusion here that a function, f known as a function already, and we know that x is the domain and y is the codomain, f has to be a subset of the Cartesian product between x and y. Yep, that's the whole point of of the module up to this point, is a function is a set. So let me say that one more time. A function is a set of two tuples where the first item of each two tuple comes from the domain and the second item of each two tuple comes from the codomain. Is that okay? All right. So given that is how we define a function with respect to the domain and the codomain, do you think it is natural to conclude that the function as a set, a function as a set, is a subset of its domain Cartesian product with its codomain? Yep. Oh, that is a very good question. Okay, let me write it down, because because we are going to cover that topic. But I'm glad that you are asking about that at this point because it is an interesting concept. So the question is this, okay, let me kind of put it in here. So the question is, I'm looking at the cardinality of, let's say, the set of all natural numbers, Cartesian product with the set of all natural numbers. So I think that is what you're asking, but I need to type it right. Keep using the wrong key. No, there you go. Okay, so you're asking about that. Oh, one is uncountably. Okay, I do not know the answer to that one, but I know the answer to this one. Okay, so you guys will kind of probably look at this and go like, no way. Okay, this turns out to be the same as the cardinality of the set of all natural numbers. The hmm? Olive, no. Yep. Okay, so we'll talk about this. Okay, because this one is kind of interesting because most people go like, well, but the dimensionality is not even the same. How can they have possibly the same cardinality? And as it turns out, it is. It has they have the same cardinality, which is olive, no. Yes, yes. Nope. There's still olive, no. We'll get to olive, no when we get to olive, no. Yes. I do not know. I cannot answer that question right away. But we will focus on this, yeah, at least. Okay, so that's kind of what we'll be doing later on, not right now, but later on. Okay, but I do want to plant the seed so that you guys look at this and go like, wow, I don't even know why that can be established. Okay, how do we establish the equivalency of two sets, each one having an infinite number of elements. And the one on the left-hand side is even worse because for every one of this thing here, it corresponds to an infinite number of over here. It's like how does this work? So we'll explain how that works in about 2 weeks or so. Yeah. No, we need functions. We need certain things about functions to explain that. So we are that's why we have to talk about functions, okay? Because we need that vocabulary to explain that. Okay. All right. So this is one requirement, okay? In order for f to be a function where x is the domain and y is a codomain, this is one requirement. If f does not satisfy this requirement, it cannot possibly be a function using x as a domain and y as a codomain. So that's the first thing you test. If you want to know whether f as a set is a function mapping from x as a domain to y as a codomain, what the mouse pointer is pointing to right now is the first test. If it fails this test, forget everything else. F cannot be a function that maps from x to y. Is that okay? So this is the first requirement. So the second requirement is this, okay? So I'm going to highlight the English sentence first, and then we'll talk about how we can express that. Each element of the domain must be mapped to one and only one element in the codomain. What does that mean? So I will give you some examples. Okay. So in this case, so highlight this, remember this sentence. Okay. It says each element of the domain must be mapped to one and only one element in the codomain in order for the set of two tuples to be a function. Okay. So I'll give you some examples. So let me go back to Joplin. Okay. So this time, so now we are working with functions. So now I am going to say, what if x is the set of ABC? Okay. Y is the set of 1, 2, 3. Okay. And the function or the set that is in question is f, and it consists of the following. Okay, well, we'll make it simple first. Okay, so the question is f a, okay, I'm going to use the notation that we used earlier, right arrow, um, oops, colon, x, right arrow, y. What is? There we go. Okay, there you go. All right, so what is the answer? Well, what kind of answer am I expecting? In other words, am I expecting a set? Am I expecting a Boolean? What kind of answer am I expecting? Is a Boolean? Yes. Nope. The domain is already X, which means that the domain is a set that has ABC in it. The sentence says for everything for each element in the domain is a set. And it's asking, is it true or is it false? That for every element in the domain, that element maps to one and only one thing in the codomain. Okay, so let's use one example here. Let's look at element A of the domain. Does it map to one and only one thing in the codomain when F is an empty set? Does anything map to anything? No. So that means we failed that condition already. And that means F as an empty set is not a function that maps the domain of ABC to the codomain of 1, 2, 3. Is that okay? It is all in the sentence. Each element of the domain must be mapped to one and only one element in the codomain. And the empty set contains no tuple, which means nothing from the domain maps to anything in the codomain, and therefore failing that condition miserably. Yes. It doesn't matter. Okay. So let's change this so that we don't use numbers. They're not numbers anymore. Oh, okay. So let's think of something that makes this true. Okay. So now we are using the same x and y. Okay. So I will go ahead and break this up. Okay. We keep the same x and y, and then we are looking at some sub cases. Okay. And we're changing what f consists of. So the next one is going to be something that's really obvious. Okay. A maps to x, um, B maps to y, C maps to z, close the set notation. Okay, and get a dollar sign. There we go. So what about this in this case? Is f a function, x being the domain and y being the codomain? Go ahead. What? Okay, I don't understand what 23 has to do with this. No, A, B, and C are just identifiers of different values. There's nothing about the ASCII code. Do not think in ASCII code in this case, ever. Done, okay? Do not, just do not. No Python, no ASCII code in this class. Yes. But we want to boil everything down to the definition. What makes a function is one, the function as a set is a subset of the Cartesian product between the domain and the codomain. Let's check that first, okay? Because if that fails, everything else is off the table. Okay, we cannot say anything. So the question now is this F, the second one, is this set a subset of the Cartesian product between X and Y in this case? Yep. Okay, cool. So it meets the first requirement. The second requirement is in words. It says for every element in the domain, it has to be mapped to one and only one thing in the codomain. So the question is, does this set of two tuples meet that requirement? So we have to look at each and every element in the domain and see if it meets the requirement. So let's start with A. Does A map to one and only one thing in the codomain? It maps to X, and X is in the codomain. Cool. We look at B. Does it map to one and only one thing in the codomain? It maps to Y, and Y is one thing in the codomain. We're good. We look at C, it maps to Z, and is Z one thing in the codomain? Yes. So now every element in the domain, A, B, and C, has met the requirement of needing to map to one and only one thing in the codomain. Okay, go ahead. Nope. In this class, we will always be given the domain and the codomain. So those are usually always given to you. and then we evaluate the properties of a function based on knowing what is the domain and what is the codomain. Yes. Mm-hmm. But that's not even the only reason. I mean, the so-called mapping, the functions that we talk about in this class, they're not mathematical functions. In other words, it's not sine, it's not cosine, it's not absolute value. It is just a general mapping of things. Okay, so I see what you mean. Yes, it's to spell it out. But a lot of times we are not even concerned about the actual mapping. We just need to know properties of the mapping. So later on, we'll see what kind of properties we want to look at. Okay, but for the time being, we just have to say, okay, does it meet the requirements? So I'm just going to give you guys more examples. So let's look at the next one. Okay, so we'll look at the next one, and this one is just kind of based on the first one, but I'm changing just a few minor details here. Okay, and I'm erasing the answer because we're trying to figure out the answer. So in this case, F is a set of two tuples, very similar to the previous one, AX, BX, CX. So now we want to answer the question first. Is this F still a subset of the Cartesian product between X and Y? Uppercase X and uppercase Y. Why not? Which one of these is not in the Cartesian product? It is. AX, BX, CX, they are all a part of the Cartesian product between X and Y, the set X and the set Y. Okay, so it has met the first requirement. The second requirement is to ask, does every element in the domain map to one and only one element in the codomain? That's a trickier question because when we look at things like this, we have implicit assumptions, okay? We have implicit requirements that is not actually part of what is specified. So if you think this is not a function because they cannot be mapped to the same thing, then you are misunderstanding the concept of each element is mapped to one and only one element in the codomain because each one is an independent question. Does A map to one element in the codomain? Yes. Does B map to one element in the codomain? Yes. Does C map to one and only one element in the codomain? Yes. So this is still a function. Yes, right. It is always mapping from the domain to the codomain. There are only two sets that you're trying to establish the mapping. Mhm. All right. So okay, so this is kind of interesting. So now we answer the question. It is true. Yep. Yep. Yeah, we will get to that. Yeah, I know what you're trying to ask, but we're going to get to that. So what if we have something like this? Okay, and I will answer the question here. Okay, so it's kind of like the other one. The first one is it a subset? Is this F a subset of the Cartesian product between set X and set Y? Yes, but it doesn't meet the second requirement. Okay, because the second requirement says for every element in the domain, there's a certain requirement. A is fine, meets that requirement. It maps to one and only one thing in the codomain. Cool. B maps to one thing in the codomain. Fine. What about this element C, which is also in the domain? It doesn't map to anything. So if it maps to nothing, that means it's mapping to zero things in the codomain, and zero is not one and only one. So element C has failed the test. Okay. So now that you have certain elements meeting, passing the test, certain elements failing the test, then the question is, how do we connect all of those tests? Are we using a conjunction to connect everything, or are we using a disjunction to connect everything? and the quantifier is for all. So which one are we using? Conjunction or disjunction? Conjunction, which means if the test fails for at least one element in the domain, then it is not a function. So this time it is not a function. So we'll say is false. Okay, so I thought there was a question somewhere. Okay, yes, go ahead. But let's be more clear. I know what you meant, but I'll just kind of add an additional clarification to it. For every element in the domain, it has to map to one and only one element in the codomain. Okay, so now let's address what you were proposing. Okay, so we are going to go like, okay, so let's go ahead and make C maps to Z, and then A also maps to Z here. So now the question is that a function? Is this F also a function? And since you're reading on this side, we're looking at this F here. Is this F a function? First test, is it a subset of the Cartesian product between X and Y? Yep, it still is, okay? The second one is, does it meet the requirement that each element of the domain maps to one and only one thing in the codomain? It has failed that requirement because when you look at element A, which is an element of the domain, it maps to X, it also maps to Z. In other words, A maps to two different elements in the codomain and therefore failing the requirement of one and only one. Now, you might ask, but why didn't you say one? I mean, it takes a little bit more spelling to spell out one and only one. Because if I said one, it is possible that someone may misinterpret it as at least one. Okay, but if I say one and only one, there's no way to misinterpret that. Yes. Okay, let's make it fail. Okay, so we'll go ahead and make that first requirement fail. So everything looks cool, and then I just decide to make this K. That would have failed the first requirement because CK as a two tuple is not an element of the Cartesian product between set X and set Y. And therefore it fails the requirement. So this is not a function. So let me answer this first, okay, because I want to make sure that I record the proper answer. Yep. Mm-hmm. Yeah, the ordering does not matter. There's no intrinsic ordering within elements of a set anyway. So there's no actual ordering to talk about between elements of a set. Oh yeah. Oh yeah. Yeah. With bigger sets, it's tedious because the cardinality of a function. Okay, so let me address that question first, and then I'll ask another question. Yep. Okay, so let's digest that. What you said is not wrong, but I can refine it. Okay, so what you said was the cardinality of a function has to be at least the cardinality of the domain, or was it the other way around? Oh, it was that. But the actual thing is the cardinality of a function has to be exactly the same as the cardinality of the domain. It's not at least. It is exactly. Exactly. Yep. Because it has to map to one and only one thing in the codomain. So there's for each element in the domain, there's exactly one two tuple in the function corresponding to it. Yes. Okay. Well, if you can think of something that is a little tricky and you want it to be answered, write it down, and then next week we can address it. Okay. Any other questions about functions right now? Okay. All right, so with 5 more minutes, I'm going to present two things, okay? The first one is, let's go back to the slide here. The first thing is, tech, this doesn't look like mathematical symbol to me. I can actually read it. Okay. You go like, okay, so what are we gonna do about this tag? You go like, okay, we're gonna derive the whole thing. That whole thing is now represented the same way as this. So that is your job, to read this chunk of text and see if you can follow the reasoning of how I can derive this to mean exactly the same thing as, for every element in the domain, it maps to one and only one thing in the codomain. Okay? This means exactly the same thing as what we talked about, except it is presented in a very awkward way. Okay? So that's one. Number two is going back to the why, because remember, this what is function as a set. How is all the mechanical stuff that we have been doing here. Now, then we have to introduce the why. Why do we have to talk about functions in such an awkward way? So I'm going to talk about something that seemingly has nothing to do with what we are doing. So let's just say that I'm a professor of CISP, say 400, and I want you to write a sorting algorithm, any sorting algorithm. As long as it gets the job done, you get the points, okay? How do I describe a sorting algorithm? In other words, if I say the input is an array with n items, n elements, how would I describe the resulting array after the sorting is done? Okay, what do you think? So the answer is actually here, okay? So the first one is we might want to use something like this to describe the result after sorting. In other words, for every valid index in the array, A is the array, and the starting of this set is 0, the ending point is a bar minus 2, and then we need this to be true for every I, which is A bracket I is less than or equal to A bracket I plus 1. Well, if I make this the requirement, I just have to initialize the entire array to 0, and I'm done. Do you guys agree? Okay. You go like, wait, but that's not what I meant by sorting, Tack. You're abusing, the description here. But I would say, but that's what you specify. I just initialize the whole array to 0, and I'm done. You cannot not give me the points if this is what you asked me to do. Okay. So now the next question is, okay, fine, I'm going to refine the description here. So to refine the description here, we kind of have to rely on something like this, which basically says if K bracket something is referencing a particular value of the incoming array, and A bracket I is the resulting array, every value of the array that you end up with has to be the same as one of the original values. Okay, so this is needed on top of this. But then you can go like, okay, well, that's easy. I will take the first element of the entire array and just replicate it throughout the entire array. It will still meet this requirement here because I did not say, because everything can map to the same value. In other words, no matter what this I is, f of I is always 0. I take the first element of the entire array, I replicate it throughout the entire array, and it is now meeting both this requirement and this requirement. And then people will go like, Tech, I think computer science is the wrong major for you. You should be a JD, right? Because I'm looking for every possible loophole, to make my job a little bit easier. But why do you need to understand all this stuff here? Especially because AI can write algorithms already. Because it is, in my opinion, that in the future, you may not be writing the algorithm, you'll be writing the specification of what it means to get the job done. So if that is your job, okay, do you want to just use the word sorting? Well, in the case of sorting, yes, okay, yeah, because it's a well understood word, we kind of know what it means. But when you, okay, if you have a job and your only responsibility is to specify what sorting means, what, how much do you think you'll be paid for that job? Spoiled peanuts, not just peanuts, but spoiled ones. Okay, rancid your peanuts. Okay, so whatever job you're going to do is going to be a lot more involving. Okay, and we cannot even express what does it mean to be the outcome of a sorting algorithm. We don't even care about the algorithm itself. I just want a single expression that is true for an algorithm that meets the requirement of what we understand as sorting. And we're still having problem with that. That is the reason why we have to talk about function and also what is injection, what is surjection, and what is bijection. Because the one piece that is missing here is F has to be bijective. Now, obviously, I haven't talked about bijection yet at this point, so I cannot, so you guys are going like, okay, we don't understand what is bijection. So that means, in your, for your weekend, okay, what I would like you to do is to read and hopefully finish reading the entire thing here, okay? It's about injection, surjection, and bijection. Okay, that's kind of your reading assignment over the weekend. And I will also unleash one of the homework assignments. Okay, it would you will have a week to work on it. Okay, it's those are all about set notation. So I'm not going to ask anything about functions, just set notations. Yep. Yeah, you can. It okay. So you're asking the result of a function is the Cartesian product of two. It's alone. That's not enough because that's one of the requirements. It is a necessary condition, but not a sufficient condition. Hmm, I'm not understanding, what you mean by that. Hmm. You can do that. I mean, you can look at Cartesian product as a function, but you can, well, okay, it's an operator. So you now have, whatever is on the left-hand side and whatever is on the right-hand side. So what you can have on the left-hand side and what you can have on the right-hand side become the domain and the codomain. Okay, so yeah. Mhm. All right, I'm gonna stop the recorder and the Zoom. All right, you too. All righty. Well, thank you for those of you who are on. We are done with the class. See you all next week. Okay, at least they signed off like right away, which means they were listening. Yes.